So far in class, we've looked at electrical modeling and we've looked at mechanical modeling. However, many systems that are useful to model are not only electrical or only mechanical. They involve a combination of electrical and mechanical components. So it's useful to have some experience and knowledge about how to model systems that are electromechanical, and they include both mechanical and electrical parts. The only difference between modeling systems that are purely mechanical or electrical and modeling systems that involve both electrical and mechanical parts is that we have to make use of certain laws that define the conversion between some electrical property and some mechanical property. In order to explain to you how this works, today we're going to model a motor. We'll assume that this motor is a DC motor and that it's a permanent magnet motor. Similar to our other modeling experiences in this class, we're going to start out by drawing a conceptual diagram of the system that we're going to model. Here's a conceptual diagram of a motor. We're going to assume that we have a battery that's providing a DC voltage because this is a DC permanent magnet motor. Inside of the motor, the motor has some resistance. So I'm going to draw a resistor that represents the resistance of the motor windings. Now the motor also has some inductance. So I'll draw an inductor. This isn't necessarily a motor that has a resistor and an inductor, but the motor windings themselves have some resistance and some inductance that you can measure in the motor, or you can look at the motor data sheet and find out the resistance and the inductance of the motor. Now, for the other component of the motor, I'm going to draw a little symbol here, like this. This symbol is representative of the stator and the rotor of the motor. So the way we're going to think about this is that this circular part is sort of like the motor shaft, and that these rectangular parts are sort of like the motor windings. Now, that's not exactly right. Remember that this is a conceptual diagram. In actuality, the resistance and the inductance are not separate of the motor windings. We're just drawing a conceptual diagram. So this part of the motor represents where the motor converts the electrical property to a mechanical property. So what I can do to represent that is to show a torque being applied in this circle, which is like the shaft. Then I'll go ahead and complete the circuit. Now the next step to model this motor is to identify the input and the output. I'm going to take the input here to be VA of t. We could also, if we wanted to, draw a switch in this motor. I'm just not going to draw the switch here at this time, but we could draw a switch to show that we can apply a step input. And the output here is going to be the torque. So I'm going to draw this as torque as a function of time. So the task that I'm trying to accomplish here is to find an equation that tells me the relationship between the input, the applied voltage, which changes over time, and torque, which also changes over time. Now, since this system includes both mechanical and electrical components, I'm going to have to use both the electrical laws and the mechanical laws that we saw in each of those individual components modeling. I'm going to need to use Kirchoff's voltage law, and for the mechanical part of this, I'm also going to need to sum the moments. or the torques, because this is a rotating mechanical system. Let's start by dealing with the electrical part. Let's apply Kirchoff's voltage law. I'm going to label the resistance R and the inductance L in this motor. And then we're going to sum the voltages. So the applied voltage at any time t is equal to the sum of the voltage lost across the resistor, the voltage across the inductor, and the voltage across the motor. Voltage across the resistor, we already saw how to do. It's the resistance times the current. Voltage across the inductor, we've also seen already. It's the inductance times the derivative of current. What about voltage across the motor? In order to deal with that, we have to apply some laws that define the relationship between the electrical and mechanical properties of the motor. We're going to apply the motor laws. There are two motor laws that are relevant. One of them is that the voltage lost across the motor at any time t is equal to a property called the motor constant times the rotational speed of the shaft at time t. The other relevant motor law defines the torque of the motor. The torque of the motor at time t is equal to the motor constant, these two are the same motor constant, times the current through the motor windings at time t. So to finish this equation that we're writing up here, we're going to use the first motor law. We have a complete equation here relating the input to other variables. However, the other variables that are on the right are not our output. Remember that the output that we defined was the torque of the motor. We have here the input, the voltage, relative to current and the rotational velocity of the shaft of the motor. How can we get these other variables in terms of torque? One thing we can do is apply the second motor law. The second motor law gives us a relationship between current at time t and torque at time t. I'm going to plug in this second motor law into this equation to get rid of current. So I've made some progress by converting current into torque, but I still have this theta dot. Theta dot is not our input or the output, so I need to get rid of that variable. In order to get rid of the theta dot, I'm going to next sum the moments. Remember, the way we do this is we set the moment of inertia times theta double dot is equal to the sum of the torques on the motor. One of the torques is our output, the torque produced by the motor windings. The other torque that we have is a torque that's due to friction. This torque will always be applied in the opposite direction as theta, so it will be negative. I'll use the parameter b, And I'm going to assume that this force of friction is a viscous friction, so it's proportional to theta dot. Now, it might seem that the next step would be to take this equation and plug it into our previous equation. However, you'll notice that I have a theta double dot here. If I substitute this in, I'll just end up with another theta double dot. So instead, what I'm going to do is I'm going to take this equation and I'm going to solve it for theta dot. Now I have an equation that relates theta dot of t to only our input and output signals. I could take this equation and plug it into this one. However, I know that I still need to get rid of this theta double dot. So before I go ahead and plug this equation in, I'm also going to take the derivative of both sides of this equation to find a relationship between theta double dot and the inputs and the outputs. Now I have a relationship both for theta dot and for theta double dot. I'm going to plug both of these equations back into this one. That completes the left-hand side of the equation. Now I need to do the right-hand side. Now, this is a pretty messy equation with lots of duplicate terms. I've got torque dot here and also here. I've got a torque expression here and also there. I'm going to gather together like terms. And I'm also going to gather together the input on the left-hand side of the equation and the output on the right. Now, just to get rid of some of these k's that are in the denominator, I'm going to multiply both sides of the equation by k squared. Now, before we try to interpret this equation, I want to go back and derive these equations in a different way. In this derivation, we assumed that the torque was the output. What if we didn't want the torque to be output? Let's suppose we wanted the rotational velocity to be the output. This is what we would want in the case where, for example, we have the motor driving a car and we want to figure out how fast the car is moving. We would care in that case about rotational velocity. I'm going to copy this diagram and redraw it below, and we're going to derive the equations that relate the input voltage to the output rotational velocity. So our new output is going to be theta dot of t. We're going to start out this modeling process the same way we did last time, by applying Kirchoff's voltage law. Now, since theta dot is our new output, we don't have to try and get rid of theta dot in this equation, but we still want to get rid of the current. In order to get rid of current, I'm going to sum the moments, just like we did last time. So J theta double dot is equal to the torque minus the damping, which we will once again assume is proportional to the rotational velocity. Now, I'm going to take torque in this equation and I'm going to replace it by using one of my motor laws. We know that torque is equal to K, the motor constant, times the current at time t. I'm going to substitute this equation into this one. This gives me a relationship between the current signal and theta dot and theta double dot. I'm going to solve this equation for I. And I'm also going to take the derivative of this equation so that I have an expression for I dot. Now, I'm going to substitute both of these equations in for my first equation, which has an I in it and an I dot. Now I'm going to multiply both sides by k in order to get it out of the denominator, and I'm going to gather together like terms. So what order is this equation? You might think that this equation is third order because we have a third derivative here. However, remember that we said that our output in this case is theta dot. Theta triple dot is only the second derivative of theta dot. So this is a second order equation, which makes this system a second order system. Let's now see if we can find something out about the relationship between voltage and rotational velocity by comparing this equation with the standard second order equation. The standard form of a second order equation looks like this. The second derivative of the output plus 2 zeta omega n times the first derivative of the output plus omega n squared times the 0th derivative of the output is equal to some gain times omega n squared times the input. Let's try and make our equation look like this one. I'm going to substitute in here the symbol omega for theta dot so we don't start to get confused with our triple dots. Theta triple dot would be omega double dot. Now, let's see if we can figure out the values of omega n and zeta using the relationship between the standard form and our equation. I'm going to start by making an association between this coefficient, omega n squared, and our coefficient here. Now that I have a value for omega n, I can find zeta by making a relationship between this term and this one. We're going to substitute in our value of omega n. Now I'm going to try and simplify. I'm going to start by squaring the numerator and the denominator. Now I'll multiply both the numerator and the denominator by JL. Now I can bring this term up to here. We can use this expression to give us some insight into the kind of response we would expect to see. For example, let's find out what conditions would cause the system to be underdamped. We know that an underdamped condition occurs when zeta is less than 1. This whole term will be less than 1 in the case where the numerator is less than the denominator. We can use a relationship like this to evaluate a particular motor to find out whether it will be underdamped, overdamped, or critically damped. And we can also use an equation like this to give us some insight as to what will happen with the response as certain parameters are changed. Let me show you an example. Notice that the value of K, the motor constant, only appears on the right-hand side. This means that as K increases, everything else being equal, the right-hand side will become larger and will eventually become larger than the left-hand side. The relationship between the voltage and the speed will then become underdamped. Also, notice that the resistance is squared on the left-hand side, but it's not squared on the right-hand side. That means that reducing the resistance will affect the left-hand side, making it smaller faster than it makes the right-hand side smaller. So, all things being equal, reducing the resistance of the motor will also tend to make the motor less damped. Once we have these equations, we can create a simulation and put in system parameters for some given motor that we want to design. We can predict the way that motor will behave in response to a step input on the voltage in order to see if the response is underdamped, overdamped, or critically damped, and whether its response is something that is desirable. In class, I'll be showing you how to create a simulation like this and evaluate motor parameters.